Hello everyone, I am Sodiris Constantinou from University of Cyprus and I welcome you to the demo presentation of the IoT Meta Control Firewall for smart buildings. According to studies, it is expected that the number of IoT devices per house will drastically increase to more than 500 smart devices by 2022. The European Union aims to be climate neutral by 2050, an economy with net zero greenhouse gas emissions. This objective is at the heart of the European Green Deal and in line with the European Union's commitment to global climate action under the Paris Agreement. Unfortunately, the CO2 pollution on information and communications technology is expected to rise from 4% to 8% by 2025. Many IoT devices enable the execution of rule automation workflows which span from simple predicate statements to procedural workflows, capturing a smart actuation pipeline in tools like IFTT, Apelio, or Apple Automation. The rule automation workflows aim to meet the convenience level of users under specific conditions. However, none of the above raw technologies enables individuals or group of users to express their convenience or comfort preferences while achieving some long-term objectives. Consider, for example, a family with a yearly budget of 8,000 kilowatt hours that aims to spend this energy budget through role automation workflows based on their configured energy consumption preferences. The family is willing to adapt its desired interior temperature preferences according to production patterns, but has no clue how the raw pipelines contribute to the target of using only 8,000 kilowatt hours per year. Our aim is to optimize both convenience and energy consumption objectives at the same time. Here we see a breakdown of our applied algorithms. The no-rule approach does not modify the behavior of the autonomous devices. Therefore, the energy consumption is minimum and the convenience error is maximum. The meta-rule algorithm satisfies all rules set by the user by completely ignoring the energy consumption. Therefore, the energy consumption is maximum and the convenience error is minimum. Furthermore, the IFTT approach executes the IFTT preferences configured by the users. And finally, the energy planner algorithm executes rules considering the trade-off between the convenience and energy consumption. The IMCF utilizes IoT data and adopts the amortization and the energy plan algorithms to meet the convenience level of users under specific conditions and at the same time meet some long-term target also configured by users. It internally deploys an artificial intelligence algorithm that exploits domain-specific operators in order to optimize the convenience and the energy consumption objectives. Our framework filters the rules of users in a way that these do not collide with the configured long-term objectives, like an actual network firewall. The amortization plan is initially executed for calculating the energy budget constraint subject to a monthly resident's energy consumption profile. There are several amortization strategies that can be used, such as the linear, balloon linear, and the ACP-based amortization formula. The energy planner utilizes the well-known hill climbing approach, searches the decision space for a solution that will optimize the user's convenience and satisfy energy constraint at the same time. However, any kind of heuristic or meta-heuristic approach can be utilized in the EP optimization step. Our system architecture comprises of a full-fledged local controller implemented inside the OpenHub stack, which is a smart home management software, and IMCF, which is a software system that encapsulates the complete application logic of the energy management stack we propose, along with the respective user interfaces. The local controller is a Java-based system installed in a micro device running on the local network of a user that will be in direct communication with the IoT devices through the OpenHub smartphone application. The complete picture can tentatively be complemented by a cloud meta controller which can enable the user to configure and run various custom rules. The IMCF has been implemented using the Open Home Automation Bus, the Linux cron tab daemon, the Anyplace for built-in modeling, as well as the Laravel PHP web framework following the model view controller architectural pattern. In our demonstration scenario that will follow, attendees will be able to observe the execution and benefits of IMCF on a graphical dashboard using pre-configured meta-rule table profiles. Users can go into OpenHub's application panel view and configure their smart IoT devices in their house. In Control Panel section, users can actually see all their pre-configured devices respectively. Under add-ons, we combine IoT devices like Daikin air condition Bosch smart fridge and cooker, Hue lighting bulbs, and many more. Navigating through OpenHub's basic UI, we can see that in our scenario, we've got a bedroom in the first floor with a smart air conditioner and lights showing their current values. Also, in the ground floor, we can see the configured kitchen and living room air conditioners along with the room lights respectively. Under the main menu, we can see the IMCF icon that directs users into our Laravel website. The user is then prompted to create an account for setting up the MetaRules table profile or logging into an existing account. After the login or register process, the users can see the configured rules in the system. For example, the first one is called the morning heat. The time duration is 4 to 7, and the action to be taken is to set the temperature level to 25 degrees. In the second case, we can see the morning lights, where the time duration is between 4 to 9, and the action to be taken is to set the light level to 40. This can be modified by clicking the Edit button and applying the changes. After we finish modifying the settings, we simply need to press the Submit button. What actually makes the difference between our system and others is that our framework gives the users the privilege to set up an annual kilowatts per hour limit. The specific example was set to 11,000 kilowatts per hour as the preferred limit. Users, of course, can change this setting by clicking again the Edit button. The users can insert new rules by clicking on the Create Meta Rule button. Then they just need to fill out the information and select one of the available options. Then, by clicking on the OpenHub local option, we can see the representation of the house using the Anyplace viewer with the configured IoT smart devices in it. We have used several points to represent the different IoT devices in our house. We can also switch from first floor to ground floor respectively. On the table below, we can see the current state and mode of our devices. The mode of our IoT devices changes automatically while the Energy Planner algorithm works on the background. The OpenHub Cloud option panel gives the privilege to the users to watch and observe the device's mode settings outside the local network. The Results tab shows a breakdown of the energy consumption, the user's convenience achieved, and the budget rate meter. As we can observe, the performance looks great. At the current state of the running program, we can see that the configured energy consumption threshold was set to 11,000 kilowatts per hour. Our artificial intelligence energy planner algorithm managed to keep user satisfaction very high and only consume approximately 9,800 kilowatts per hour by also keeping the user within the budget. Below we can see a breakdown of the energy consumption budget. The orange color shows the 90% of the budget that has been consumed. We can also see that 10% out of the budget is still available and ready to be consumed. The table at the bottom shows a more detailed analysis based on the results. As we mentioned before, the total energy consumption is approximately 9,800 kilowatt hours. The total average and convenience average errors are 2.75%. The residents of the example scenario haven't used any more energy than the pre-configured constraint, and therefore the budget average is 0%. The users also have the privilege to observe their individual convenience average error based on their configured meta rules. In this case, Soderis had 1.57% average convenience error and Adonis only 1.18%. This is the end of our presentation. Thank you very much for watching.